Yield lines special cases. This video deals with rectangular slabs with 2-point supports and one fixed end support. Situation like this, it's a slab A times B, B between A and 2A, and 2-point supports. It's loaded by a uniform distributed load Q. To find the maximum bending moment, we first look up the axis of rotation, which is for the point support something like that, and from the other side something like that. And at the support here, then we have an axis of rotation like this. Because of symmetry around the YY axis, we know that the yield line must come through the intersection of the two rotation axes, and it will be vertical because of the symmetry around YY. So this is the direction of the yield line. The right-hand side, the yield line or direction of the yield line starts at the intersection of the two rotation axes, but we do not know the angle. So that's one parameter that we have to optimize. We don't know this parameter. We have a parameter alpha, but also we have this angle, which is not known. So the direction or the slope of this rotation axis can vary too. Instead of taking alpha only this and then beta the total, we take alpha plus beta is the slope is the difference in slope of the two axes of rotation. Because of the symmetry around YY, of course, left and right is the same. Then we can draw the yield lines. It stops at the end of the slab. And then now we have the three yield lines. We see also that we have two parameters, alpha and beta. That gives you the right position of those yield lines. So the parameters is x1 in tangents of the angle alpha, alpha in degrees, and beta is also in degrees. So x2 is the tangents of beta and x1 is the tangents of alpha. Then we can identify some geometric characteristics. And the main idea is that all the characteristics that we need for calculating the virtual work done should be expressed in our two parameters that we've chosen, alpha and beta, so that we can maximize the function afterwards. We have a geometric parameter and we call it mu, which is b equals mu times a. This is so that you can use the different formulas for different shapes of rectangular slabs. But mu is not playing a role in the maximization of the function. Don't forget that. Cosinus alpha can be expressed in a function of tangents alpha, so it's easy to express it in function of x1. Sinus alpha, the same. The tangents gamma is in fact equal to the cotangents of alpha plus beta. This can be expressed in a function of tangents alpha and beta, and you have this expression. And the tangents of alpha plus beta is equal to this expression. The cosinus of the summation alpha plus beta, we will need it in the expressions of E and D, can also be expressed in function of x1 and x2. We will use all those relationships in the following slides. S4, this is S4, is of course, if you this angle is alpha plus beta, so the tangents of this angle is equal to S4 divided by B over 2. And then you can express it in x1 and x2. S6, we use the cotangents rule. It is the base S2 divided by the summation of the cotangents of the two adjacent angles. And we can go on. Every parameter can now be expressed or every variable can be expressed in the parameters x1 and x2 and mu. So we can go on with every, for instance, tangles of alpha plus beta is, of course, equal to S4 plus A divided by S3 plus B over 2. This is B over 2, and I've cut the picture in half. And so you can continue expressing all geometric parameters in function of x1 and x2. Again, for H3, we have used the cotangles rule, but it's getting sometimes a little bit complicated. Then when we have all those parameters, geometric parameters in function of x1 and x2 and mu, we can start calculating the work done by the external forces. It's E divided by delta Q. And then you will see that we are working with triangles. For instance, take this triangle. The surface of this triangle is H1 times its base, which is B plus 2S3 divided by 2. And the mean deflection is H1 divided by 3. But now we must subtract those parts of the triangle which is outside the slab. So this means that we have to subtract A1 times S3 divided by 2, multiplied by the maximum deflection here, divided by 3. So the maximum deflection is A1 divided by H1 and then divided by 3. And the same for this side. So now for each triangle, this is the main triangle, then there's another one here. You can do the same exercise. And for this triangle too, you can do the same exercise. For instance, for this triangle, it will be H3 times H times S2 plus S1 divided by 2 and divided by 3 because it's the maximum deflection delta over 3. And we subtract this, which is S1 times S5 divided by 2 times the maximum deflection divided by 3, and the maximum deflection is S5 divided by H3, and the same for the other side. So you see, so you can, in a very easy way, instead of using integrals, you can, in this very easy way, calculate the work done by the external forces. Now we simplified a little bit this formula, because when you express it in x1 and x2 explicitly, it will be a very long formula, which is almost not usable. So we keep it like it is there. The work done by the internal forces is then this yield line projected around this axis of rotation gives you B times the angle of rotation delta divided by H1. So that's this one. The negative bending moment gives you the same. It's projected on this axis of rotation, so it's B, and the angle of rotation is delta over H1. And then we got this portion projected on the axis of rotation. So it's the length is S7 divided by the angle of rotation, which is delta over H3, and we got it 2 times left and right. So that's this formula. So the only difference with the video 8 is that this is becoming 2 instead of 1 because of this yield line. So m is a function of alpha, beta, and mu, and is equal to q multiplied by E divided by D. But we have to satisfy some conditions. The first one is H1 must be smaller than A, so the intersection of the yield lines must be inside the slab, of course, and A1 must be positive. And of course, alpha plus beta must be smaller than 90 degrees. So it means that every point, alpha and beta on this graph, the sum of it must be smaller than 90 degrees. For H1, we can use the expression of x1 and and make inequality, making it smaller than a, and you call the maximum value of x2 x2m, and then x2m is then a function of alpha and mu, or a function of x1. Right? So this is nothing else than h1 expressed as h1 is equal to a, and then you get 2 out of it, and this is called x2m. It gives you on this graph, you can see it. This is alpha, and this is beta, or this is x2, but in the limit value x2m. And for each mu, we have a drawing like that. For instance, or a graph like that. You have the red one, it's for mu equals 1, which is a square slab. Blue curve is for mu equals 1.5, and the black one is for mu equals 2. So those three curves, you have to be on the left hand, every combination on the left hand side of this curve will be fine. On the other hand, we will have the condition A1 must be positive. So this is the value of A1. This is only possible. This is only possible if x2 is bigger than 1 over x1, or I call is this value, the maximum value, x2n is equal to 1 over x1. And this is plotted in this color, and it's given you this line. It means that every combination is only valid if it's on the left-hand side of this curve, because this curve gives you the condition A1 positive. Those three gives you the condition H1 is smaller than A. So now we can give an example. Again, these are the curves for mu 1, 1.5, and 2, and this is for H1 positive. So now we have to make some combinations of alpha, beta, and mu to see where is it valid. To give you an idea, suppose we have alpha 50 degrees and beta 30 degrees for a square slab. It looks like that. Huh? Then we see that this is alpha is 50, beta is 30. We are here on this side, but it's for a square slab. So the red curve is valid. We must be on the left-hand side of the left curve. That's fine. And on the left-hand side of this to make E1 positive. So at this point, it's okay. You can take a second example. For instance, for the black curve, we have a alpha 1 of alpha is 60, and beta is also is 50 degrees. So we end up here on top. So we see that we are now first on the left-hand side of the blue curve. So that's fine. But we are on the right side of this curve. So it's not okay, because you can easily see A1 now is negative. Where this yield line is cutting this edge, you see this is negative. So it's not okay. And a second example, for instance, when you have a combination for the black curve where mu is 2, then we must stay on the left-hand side of the black curve. So 20 degrees is okay. And we do not have to worry of if A1 must be positive or not, because we are almost on the left-hand side. So you see, it's sometimes a little bit complicated to see which valid combinations of alpha, beta, mu are allowed or are there. So what we will do to make it easy, we will say that this area, we will work in this area. Then we know we don't have to worry about this A1 positive restriction. And we only have to worry, we try to stay on the left-hand side of this black curve. Then we are sure we are in a right position. So the scale factor now of this graph is QH squared is taken as 25. Alpha is between 0 and 40 degrees. And we plotted different curves for beta. And then we take mu. The mathematics can make the same graph for mu is 1 or mu is 2. And we take here for mu is 1.5. For this type of slab, we see to the different curves that, yes, we will reach somewhere a maximum. It's not for this point. So you have for each curve you have a combination of alpha and beta that gives you a maximum. But we are looking for the maximum of those. So you will see from the red curve, the blue curve, and so on, you have different maxima. We see that somewhere here, there is a maximum because the blue curve, this, is already descending. The maximum is less than the others. So we blow this up. You can see it on the axis, and this is 2.3, 2.4. So this is somewhere here. Huh? And alpha is between, let's say, 20 or 22 and 32 degrees from there to there. So it's this portion. You will see now, if you only vary by 1 degree in beta, you have different curves reaching all a maximum, but they will, when alpha 2 of beta must be smaller than 23 because this maximum is already going down. And from this curve, you can now easily indicate the maximum, and the maximum is found at alpha 27 degrees there, and beta 21 degrees. So it is the magenta colored curve that gives you the maximum. And for a slab of 1.5 in mu parameter. We can make this procedure to find the maximum of the bending moment, and we have done that now for mu is equal to 1.5, but now we will do it the same for mu is 1, 1.25, and so on. For all those different points, we look up the maximum value. Now, we check that this table is valid because it's possible that the combination of those alphas and betas are not valid. So we plot those values here, and we see that we all stay on the left-hand side of the black curve. The black curve was for alpha equals 2. So we are confident that all those combinations are valid. So what we will do now is, it is when calculating maximum bending moment, it's easy to express it as the total load divided by a coefficient. So it's QAB, that's total load divided by a coefficient. So I calculate this coefficient and plot it in a graph. So it's in function of mu from 1 to 2, because mu bigger than 2, it makes almost no sense, the yield lines. And then I've plotted all those values of K using this table. We make a regression, and we find that the relationship of K is 9 times mu plus 2.23. So this means that the maximum bending moment is now expressed as a function of mu, which is the total load divided by K mu, but B is mu times alpha. So everything is expressed in Q8 squared times mu divided by the coefficient K mu. So now this is an easy expression to calculate the maximum bending moment of each situation. For a square slab, for instance, mu is 1, so M max is Q8 squared divided by 11.23. We can now give you a small example how this works. We have a slab 6 by 4 meters, fixed end support and 2 point supports, loaded by 20 kilonewtons per square meter. Mu is 1.5. Alpha is 27 degrees, and this is 21 degrees. And this is the alpha and the beta, or the x1 and the x2, with mu equals to 1.5. And the K value, 1.5, you can calculate it now directly. It's 9 times mu plus 2.23 is 15.7. So the maximum bending moment is Q8 squared times mu divided by K. And it gives you 30.5 kilonewton meters per meter. When you compare this with the video 8, and video 8 is about this being simply supported, then you see that when this is fixed, that the A1 increases. So this portion of the yield lines, it gets bigger, which is normal because the fixed end support attracts more weight on this side.